Hello, everyone, and welcome to today's webinar. I'm Deanna McNeil, Associate Science Editor for The Scientist, and I'll be moderating our discussion. Today, our speaker, Ikuro Suzuki, will share case studies related to his team's findings, introducing approaches for peripheral neurotoxicity evaluation, mechanism of action prediction using artificial intelligence, and microphysiological systems that integrate microelectrode arrays with microfluidic channels. Before we begin, I'd like to thank Axion Biosystems for sponsoring today's webinar. We like our webinars to be interactive. We encourage you to send us your questions or comments at any point, and our speaker will address these during the Q&A session following the presentation. To ask a question, simply click on the Q&A tab and type your query into the question box located on the right side of your screen. Our sponsor has provided us with some helpful resources related to today's webinar, and we've posted these in our handout section on the right side of your screen. You can access and download these documents at any time during the webinar. And if you've minimized the Q&A panel, simply click on the blue chat button in the bottom right corner to bring it back. This webinar will be archived on the Scientist website, and we'll send you the link via email within a couple of days. Please note that you will not be able to download the presentation slides. And with that, let me introduce our speaker. Ikuro Suzuki is a professor in the Department of Electronics and Graduate School of Engineering at Tohoku Institute of Technology. He received a PhD from University of Tokyo and previously served as an assistant professor at Tokyo University of Technology and at Tokyo Medical and Dental University. Suzuki's current research focuses on developing in vitro electronic sensing and 3D tissue reconstruction techniques for brain function studies, drug discovery, and regenerative medicine. Let's make sure that our slides are up and running. Excellent. Take it away.
Hello everyone, my name is Ikuro Suzuki from Tokyo Institute of Technology, Japan. It's truly an honor to be here today and to have the opportunity to present this Action webinars. I'd like to thank the Action Biosystem team for kind invitation and for their wonderful support. Today, I will be presenting talk titles, Evaluating Neurotoxicity Risk with Microelectrode Arrays. In recent years, the term New Approach Method or NAMs has become increasingly common. NAMs refer to a broad range of technologies, such as in vitro assay and AI-based in silico models, that are designed to replace or complement animal testing for chemical and drug safety assessment. In Nature-reviewed drug discovery this year, the use of NAMs in the non-clinical stage of drug development was clearly highlighted. Importantly, NAMs are not only safety assessment, they are also valuable for screening and efficacy testing of candidate compounds, and are already being adopted in-house in many pharmaceutical companies. So NAMs are no longer new, they are becoming part of our everyday experimental toolkit. Regulatory acceptance of NAMs is also progressing rapidly in the revision of ICH S7A guideline, which covered pharmaceutical safety pharmacologies. It is stated that remarkable scientific and technological advance has been made in the field of pharmaceutical safety science, particularly in the area of new approach methodologies. To ensure these technologies are accepted, we must continue to demonstrate validation, reproducibility, and reliabilities. But I believe it's only a matter of time before in vitro evaluation are routinely integrated in regulatory frameworks around the world. At the OECD's, discussions are underway to introduce in vitro methods for developing developmental neurotoxicity (DNT) assessment. 70 assays have been proposed, covers the major process of neural developments, proliferation, differentiation, synaptogenesis, and functional network formation. The goal is to establish guidance for how in vitro DMT data should be interpreted and integrated into regulatory decision-making. Among various NAMs, microelectrode array (MEA) is one of most established in vitro functional assays, with history of over 15 years. Today's Action Maestro system is most widely used MEA platform worldwide, typically with 60 electrodes per well in the 48 well format. In our lab, we reported MEA recording from rat primary hippocampal neurons as early as 2003, and in 2013, we became the first in the world to report drug-induced response in human iPSC-derived neurons. Since then, we have evaluated over 100 types of human iPSC-derived neurons and more than 1,000 compounds. And in 2023, we established a CRO company, Vitrolabo, to further promote MEA-based drug safety and efficacy testing. Today, I'd like to share several topics related to compound safety evaluation. One, seizure liability prediction in pharmaceuticals and toxicity risk assessment of pesticides. 2. AI-based analysis for toxicity risk and the mechanism of action prediction. 3. Evaluation of addictive compounds using chronic and acute paradigms. 4. And finally, MEA-based microphysiological system, MPS, combined with microfluidic channels. When human iPSC-derived cortical neurons were cultured on MEAs, we can observe spontaneous network bursts that reflect synchronized neural network activities. When we applied 4AP, a potassium channel blocker known to induce seizures, both raster plot and firing histogram show clear increase in spike count and burst frequency. Of course, not all seizure-genic compounds produce the same pattern. Each has its own signature, depending on its mechanism. From these raster plots, we can calculate many quantitative parameters. Here we show 9 representative ones, such as total spike, number of network bursts, burst interval, burst duration, and spikes per burst. In total, we can extract over 100 parameters, but around 10 to 20 are sufficient for robust evaluation. This heat map shows the data from 10 seizure-positive compounds and 4 negatives, analyzed in both rat and human iPSC-derived neurons. Red indicate parameter increase, blue indicate decrease, and asterisk denote statistical significance. You can see that the pattern differs between species. However, this does not represent the difference between rat and human cells, as human cells also respond differently to difficult benders, as different benders have a different balance of excitatory and inhibitory neurons. What matters is not whether a single parameter changes, but how we interpreted the overall pattern. Which brings us to our next step, risk evaluation. So we use principal component analysis PCA with DIMSO's standard deviation range as baseline. Compound widths in the SD range are defined as low risk, beyond 1 SD as middle risk, and beyond 2 SD as high risk. DIMSO and the negative compound acetaminophen remain within SD range, even as dose increased. For example, HOAP and aminophylline clearly deviated from baseline in dose-dependent manners. The table below shows risk notation by dose. These are dose-dependent risk results for seizure-positive compound. Alert are rise for all compound. In contrast, a negative compound were jet negative, even as dose increase. What is important is whether in vitro seizure risk reflects in vivo. To verify this, we conducted animal experiment in that, measuring CSF concentration at the time seizure was observed, and at the time tremor, a prodrome of seizures, was observed. We then compared our in vitro MEA-derived toxic dose with in vivo CSF concentrations. In this graph, the y-axis is the toxic dose predicted by our MEA, and x-axis is the CSF concentration. Because the dose was spaced by a ratio of 3, plotting on y equal x indicated agreements. In rat and human iPSC-derived neurons, the predicted toxic dose from MEA matched remarkably well with CSF data, demonstrating that our in vitro model can reflect the in vivo seizure threshold. Pilocarpine, being observed at low concentration in MEA, is known to be due to the strong influence of astrocytes in vitro conditions. So we consider that in vitro MEA measurement and our PCA method are powerful tools to predict in vivo seizure risk. The current topic regarding seizure liability is summarized in these papers. Next, I will discuss OECD toxicity evaluation for pesticides. This slide shows the 17 assays under consideration for developmental neurotoxicities. For functional network evaluation, MEA testing is included. In DNT assessment, a chronic exposure that measures the time course change under compound exposure is also effective. However, considering system stabilities, we think acute exposure tests can sufficiently evaluate the DNT as well. We evaluated 10 peptide compounds and 2 negatives using nucleoside human iPS-derived cortical neurons, the same as the in-seizure assessment. The mechanism included a nicotinic acetylcholine receptor agonist, choline esterase inhibitors, GABA receptor antagonists, and sodium channel openers. Toxicity risk was evaluated as in-seizure assessment by deviation from the DIMSO-SD range. Negative compounds were judged as negative, even when dose increased. For peptide-related compound, dose-dependent deviation from SD range was observed. The figure on the left shows the data for all 10 compounds, and the right shows the change for each compound. The table on the left shows the dose-dependent toxicity risk for 10 peptides. So using PCA, we found that response is clustered according to mechanism of action. Acetylcholine-related compound in the centers, GABA antagonists in lower left and sodium channel opener in upper left. When we added validation compounds, they plotted in some regions, indicated that MEA assay can not only assess toxicity risk, but also predicts the mechanism of actions. Next, I will talk about AI analysis. Our laboratory has developed various AI-based analytical methods. Here, I introduce one using raster plots. Because AI has high discrimination capabilities, we trained it using raster plot to classify toxicity risk. This slide shows the training and prediction scheme. Raster plots were divided and input into pre-trained CNN model to extract future data. Together with toxicity labelings, we trained a new AI model. For untrained test data, the features were extracted similarly and input the trained model for toxicity prediction. These are results for trained compound data. The positive compound shows dose-dependent seizure risk, and the tests were unseen by AI were similarly classified. Predicted toxic dose also matched a CSF concentration observed in seizures. So negative compounds were correctly judged negatives, even at higher dose. Next, for compounds not included in training data, AI also produced dose-dependent risk prediction for seizure-positive compounds. For example, picrotoxin was classified as risky at 0.1 micromolars, consistent with in vivo seizure concentration near 0.3 micromolar. Theophylline shows only slight risk, even at 30 micromolars, consistent with seizure onset above 300 micromolar in vivo. In short, AI taught us that our dose setting were too low. Sometimes the machine is wiser, colleague. This slide compares conventional parameter analysis and AI analysis for negative compounds. In conventional approach, focusing on individual parameters can sometimes lead to false significance. However, the AI correctly classified all negatives as safe, suggesting that it comprehensively interprets network behavior rather than single parameters. Next, I will discuss compound name prediction for mechanism of action analysis. From rasters divided features, AI estimated 40 compounds using leave out one approach. For each compound, we trained the model, excluded one well, and then predicted the excluded data, creating 20 models for compound and averaging their outputs. All vehicle wells were correctly classified as vehicle, indicating the AI was identifying compound-specific patterns, not well artifacts. As the dose increased, the AI predicts compound identities with nearly 100% accuracy. So negative compounds remained negatives. This approach also succeeded in predicting mechanism of candidate compounds provided by pharmaceutical companies. We therefore consider AI analysis highly effective for MOA prediction. Next, I will discuss assessment of addiction compounds. We chronically administered 6 addictive, 3 non-addictive, and 2 negative compounds for 10 days, starting on day 35 of culture of CDI dopaminergic neurons. Nicotine and varenicline share the same primary mechanisms. The upper panel shows the concentration used for chronic exposure. The lower panel shows the cumulative dose before and after chronic administration. So we evaluated addiction-related effect by comparing change in acute responses before and after chronic dosing. These data show dose-dependent responses before chronic dosing with nicotine and varenicline. With increasing concentration, both nicotine and varenicline increase network burst. However, nicotine increase spike count, while varenicline decrease them. These are cumulative dose results before and after chronic administration for addictive compounds. You can see that responsive pattern changed. For ethanol, a firing disappears after chronic exposure at 3 micromolars. Here are changes for non-addictive compounds. Compared to addictive compounds, changes were less pronounced. Dimsol and acetaminophen show minimal variation. Since culture duration also influences results, we use PCA to differentiate between addictive and non-addictive characteristics. Using PCA, we analyze change before and after chronic dosing. Circle indicates preclinical dose response, and the square indicates post-chronic. Addictive compounds such as nicotine, ethanol, flunitrazepam, phenobarbital, methamphetamine shows distinct shifts. Non-addictive compounds such as varenicline, mushmol, and amantadine, as well as negatives dimsol and acetaminophen, show little change. We then quantify this change using Euclidean distance between pre- and post-chronic conditions. For addictive compound, distance increase dose-dependently. For non-addictive compound, no such increase was observed. We set the threshold at 2 SD of dimsol's pre-post-chronic distance. As a result, all 5 addictive compounds shows dose-dependent toxicity risk, while non-addictive compounds were just non-risky. This slide shows the results from reproducibility experiments conducted on another days. So we again detected risk for addictive compounds and no risk for non-addictive compounds. So these results confirm that our MEA system is effective for addiction assessments. After MEA measurement, we examined receptor expressions. Nicotine receptor levels were generally similar after chronic nicotine and varenicline exposures, consistent with animal studies. In contrast, dopamine and GABA receptor expression significantly increased after chronic nicotine treatment compared to varenicline. So these results also agree with animal data, showing that in vitro chronic exposures using human iPSC-derived neurons reproduce in vivo receptor changes. Finally, I will discuss MEA-based microphysiological system, MPS, combined with microphysical channels. Also, MEA patterning using PDMS microchannels has long been reported. We developed a COP-based device that avoids compound adsorptions with 2 chambers connected by microchannels. These channels allow us to connect different cell types, and importantly, the media of 2 chambers do not mix. Simulation confirms that even after 3 days, mixed was only 0.3%, and actually image confirmed no medium crossovers. This MEA device enables the evaluation of interaction between cell types with different media requirements and support construction of neural projection models that mimic in vivo connectivities. We have developed several projection models, synaptic transmission model in central nervous system, neuromuscular junction model of motor neuron and skeletal muscle, the sensory neurons, spinal cord, pain model, and myelination model. In synaptic transmission model, hippocampal and cortical neuron were cultured in separate chambers. New light extends through the microchannel and forms synapses. The left two columns shows hippocampal activities. The middle four correspond to microchannel regions, and the right two show cortical activities. The signal-to-noise ratio is highest within microchannels due to increased seal resistance, allowing high-quality signal detection. When picrotoxin, a GABA receptor antagonist, is applied to hippocampal site, network burst frequency increases. The cortical neurons also fire more frequently in synchrony with hippocampal burst, indicates the enhanced synaptic transmission from hippocampus to cortex. Increase in firing was also confirmed within microchannels. So this system can thus be applied to various projection pathways of CNS. In another example, sensory neuron cultures in one chamber extended neurites through microchannel into the opposite site, creating configurations where only new sites were present in second chambers. Since sensory stimuli were received by neurite in vivo, this setup mimics physiological sensory transmissions. Because many sensory neurons were quiescent without stimulation, baseline activity is low. However, upon applying AITC, which is TRPA1 agonist, numerous spikes appear immediately after application. Prominent signal change within microchannels indicated that a microchannel also improved detection sensitivities. Summary: in vitro toxic dose correlated well with in vivo CSF concentration, demonstrating strong translational potentials. AI-based analysis was effective not only for toxicity risk prediction, but also for mechanisms of action identification. Combining chronic and acute testing enabled detection of addictive compounds, and MEA-based microphysiological systems successfully models neural projection networks. All of this work is the result of the dedication of Suzuki laboratory members, and I want to thank them sincerely for their effort and creativity. These assays also conducted at Seattle company Visual Lab. Thank you very much for your attention.
Excellent. Thank you for that presentation. I'd now like to introduce Bumpei Noda, a researcher in Dr. Suzuki's lab, who will be filling in during today's Q&A session. Thank you for joining us, Bumpei.
Thank you for introduction.
Excellent. We do have some questions, so let's go ahead and jump into the Q&A. A variety of cells are used, but are there any standardized parameters for evaluating the safety of compounds?
Sure. The parameters by which compound responses are detected vary depending on the mechanism of actions of compounds and cell characteristics themselves. It's necessary to select the parameters appropriate for the purpose. When using the same consistent quality cells and conducting seizure liability assessment, I believe standard parameters can be determined to a certain extent. When considering a regulatory implementation in future, I believe it is necessary to determine standard parameters for the easier assay and calculation.
Perfect. Thank you. Is there a possibility that MEA assays will be introduced into regulation?
Sure, yeah, I believe it's quite possible. The Hazy Neurotoxicity, what's a global industry academia consortium, is currently compiling the data across multiple sites from pharmaceutical companies, CRO company, as well as our academic institutes. So since it is under also consideration by the OECD we mentioned, there's a strong possibility that the MEA-based seizure liability assessment could be introduced into ICH in the future.
Great. How big are the microfluidic chambers? Are they custom made for the MEA and cells?
That's a good question. So we are actively adjusting the microfluidic channel sizes, but I believe it's about a few times bigger than the Action's electrode. So it could be a few tens of micrometer. I don't remember the exact figure, but I can go back to the questioners later if necessary.
Perfect.
Oh, by the way, it's yes, custom made, and we are actively developing. If there is any feedback, you can send us, shoot us any email from your experience or suggestion. And then, by the way, we are going to present these results at the Society for Neuroscience in San Diego, so we can interact or discuss interactively.
Perfect. Yeah, we'll share the speaker's contact info at the end of the Q&A, so definitely feel free to reach out.
Yes.
Let's see. What other biological models can be constructed using the MEA and MPS?
Sure. So although we did not cover, some of the models we are actually developing, we are actually constructing the models of, as showed the neuromuscular junction pain models, and also the sympathetic myocardial projection models, which are in high demand from pharmaceutical companies. So we can measure intercellular interaction in samples that cannot be co-cultured in the same medium condition. And since numerous neural projection pathway exists, application range of the MPS MEA combinations are very broad. And we are welcome to have new suggestions or ideas to have an interactive discussion.
Fantastic. What is the throughput of your assay for large-scale screening?
So for the CRO company, we believe our current maximum throughput could be like 100 compounds at the same sample, which is actually done by our government-sponsored project. So it's about maybe 10, 20 plates, Action MEA plates.
Perfect. And what is the longest duration that you can perform the assessment?
It depends on how we culture cells. For example, if we culture 3D organoids, we can culture like a year or more. If 2D culture, as you may know, the cells started to aggregate. So typically we use the cells, neurons at week 4 to 5 for 2D cultures. And for 3D organoid cultures, we typically use after 100 days, so about 14 or 15 weeks later from the IPS differentiation.
Perfect. Thank you. And do you consider shear stress in the microfluidic system?
That's a good question. I believe there will be, but I haven't discussed internally, but I think that's a possibility. But It could be pronounced in impedance or cell viability. We can check.
Excellent. And how do you select cells that are suitable for evaluation? So, for example, glutanergic versus GABA neurons.
Yeah, so the excitatory or inhibitory balance in the living cerebral cortex is approximately 8 to 2. So gluta is 8, GABA is 2. So we typically use the human PSC neuron with the similar ratio. In fact, model closer to this in vivo balance exhibit better drug responsive and the toxicity dose has in vivo exploration potential. While it depends on the objective, the presence of a GABA neuron is essential for predicting seizure liability.
Excellent. Well, thank you so much, Pompey. I think that is all the questions we have time for today. We really appreciate you joining us.
Great.
If anyone has further questions, please do consider reaching out to the speaker directly. And as mentioned, their contact is shown on the screen. As a reminder, the webinar will be archived on the Scientist website, and you'll receive an email notifying you when the on-demand webinar is available. Please make sure to follow the Scientist on social media for updates on future webinars. I'd like to thank everyone who took the time to join us today, and particularly those of you who shared your questions and comments. On behalf of the Scientist, I'd also like to thank our speaker, Ikuro Suzuki, and Pompey Noda, as well as our sponsor, Axion Biosystems. Thanks so much, everyone, and goodbye.